Right, so yes. Yeah, something. Hello. Yeah. Good evening, everyone. So our topic is generative attribution, and I am Ananya, Pulkit, and Ashish, and our guide is Vishak. So first, I will introduce. First, I will introduce you to what is actually the paradigm and what is generative retrieval. So currently, there are two. There are the techniques that exist for fetching the documents for query related to LLM. They do a semantic search between the text embeddings and the documents that are present. In the current approach, what we are trying to do in the generative attribution is that we have a set of existing documents and their doc IDs, and we want a large language model to generate the doc IDs corresponding to that query. So we will discuss the three papers, and this is the first one of uh, one of the paper called Hierarchical Category Path Enhanced Generative Retrieval. So next slide.
So what is important is, even if, let's say, you don't find a suitable venue, like you'll see most of these papers are put on archive and they're not even necessarily accepted. At the least, the paper should be on archive at the end of I mean, it's a margin after your final presentation.
Yeah. So the problem that paper tries to solve is that the models that exist in the current paradigm, the generative attribution, is that they directly decode the doc IDs and do not provide any explanations to why a particular document is fetched. The solution which is proposed in this paper is that we can also generate the paths, like how the doc IDs is generated, how the model is thinking. On the similar lines, we can generate the paths, and the claim is that this will also improve the retrieval performance. So suppose like in the normal system, the user asks the query, when was the Dubai founded, or what are the economic sectors of Dubai. The documents are the doc IDs are directly fetched, and there can be different kinds of doc IDs. It can be textual that makes sense more to the human. It can be related to the numbers or embedding based, which makes sense to the language models. So next slide. Now, how are the paths being constructed is that the Wikipedia, it has organized its information in the form of tree and goes from the high level category to lower level categories to fetch a particular document. And the idea is to linearize the tree structure using the delimiters, because large language model could not understand the tree. And by using the delimiters, we can just create the paths, and all the paths are stored in set T. So this is how the categorical path construction works in this. There is a category tree here, and for a document capital D, which is our particular document, first we have two steps in this process. The first is that uh, like the pre-candidate path construction set, in which we list out all the paths that we have created using linearizing, and then pick a particular document D, pass both into the pass both into the encoder, and see what is the maximum similarity. We choose the top k paths associated with a particular document. Now these k paths are chosen, and it is given to a large language model, which then decides that large language model chooses the top three paths associated with the document capital D. Next. Yeah, so this is I already explained this slide. Next. So the task on which the model is trained is, there are two tasks on which the model is trained: the indexing task and the retrieval task. So indexing means that you are first given a corpus of documents, and capital D represents document, small d represents the document ID corresponding to that document, and we have generative model capital M. The task should be that we give a document capital D, and the output should be the document identifier small d. Here, the n in the first represents the number of tokens of that particular doc ID, and this is like a normal multiplication of probabilities to get what is the probability of getting a doc ID D for that document capital D. The next is the retrieval task, in which we give the model query Q, and in return it should give you the most relevant doc ID D, small d. Next. So now for the training purposes, we have the
Maybe I'm jumping ahead to the previous slide. So is this process the previous slide? This is auto-regressive.
yeah, it happens token by token, and in the inference they do beam search.
I see.
Yeah. So for the training purposes, we take the existing training set, which consists of the query document capital D and its doc ID D, and augment it with its most relevant path, which is denoted by the PQ here. So for creating this, what we do is that we have made this set P of D, which came in the previous slide before. It is basically that for a document D, you have the three most relevant paths associated with it, and for each path, the three paths, we are seeing that which has the highest similarity between the query and that path, and then choosing the maximum similarity one, we associated with this and create the new training set X plus. Now for optimization, we what we do is that we take this training set X plus and we train our model on the two tasks, indexing and the retrieval. These are simple negative log likelihood of the negative log likelihood of the previous losses that I described earlier. In this, we are summing for the all three documents that the authors have chosen as a hyperparameter, and the retrieval loss is also like negative log of given a query, what should be the path and the doc ID D. So important thing is that in this we are giving document D. Now we are generating both path and the doc ID D. We are giving query. Now we are generating both path and along with the document ID D. So finally, the total loss on which they are
Yeah, but for
optimizing.
the indexing loss, isn't low? Isn't like you may have your critique, but isn't log likelihood too simplistic? Because what might happen is you may land up index. I mean, you'll be swayed by the most popular uh, D, right?
So there could be like making regularizations in this loss term. They are just simply taking the negative log likelihood.
This looks too trivial to me. I mean,
They have not provided anything else in the
is your project to trying to make it more principled? What is your? I mean, is it connected to this or no?
the project.
Hmm.
The project is different. Like we just want to introduce the three papers in the seminar and take their key ideas
Is
and
it is this something you'll address in your project?
the log loss function.
Yeah, the
Um,
indexing law, which I'm not happy about at all.
no, this loss will not like this loss
Indexing
will
law,
be different.
indexing is a filter, right? If
This will
indexing
be
goes wrong, what will you do with it?
yeah.
Right? So there's a bottleneck in indexing. I'm not convinced this works at all. This will just swayed by the most popular. Vishak, this will just be swayed by the most. Sorry? So you're saying the project, but this paper, I'm talking about a critique of this paper. Do you agree with my critique or no? Or do you have your own critique, which is also fine?
Yeah, like the idea is that from this paper we can take their idea that we can
No,
construct the
critique,
paths.
critique.
Yeah,
Is there a
critique
critique
is
on this paper?
fine. Yeah, it is very simple. The whole paper just consists of the two log the loss terms, which are just negative log likelihood and nothing else. So finally,
Yeah, but your critique has to be more specific than that. Na? Like my concern is may get swayed by the most popular, the most frequent index. Right. So how do you can you put some regularization? Regularization certainly is lacking here, but some structure to that regularization might be even more interesting. Okay, go ahead.
what we can include in this that they in the Wikipedia articles there are also grades that Ashish will talk about. So the articles are divided into the grade. We can incorporate into it, and we can in the loss term we can like apply a more penalty on the lower grade term. So that could also be done. This. So finally, after training this, they claim that it will learn all the relations between the path, doc ID document, and the query. Next. Now, in the inference setting, what they do is that the model takes the query Q and inference is divided into two stages: the path generation stage and the doc ID decoding stage. So for the path in the first stage, what the suppose we are given a query to the generative model m theta, it will generate p paths. It will generate up to sorry, not p, the k paths using the beam search. And now for all these paths, what we are doing, we give a particular path to the model m, and we will generate the m doc IDs associated with that particular path. So, and finally, then we will choose the doc ID with the maximum score, uh, and we will have the list of the k documents of different paths. Like we have k different paths, and we have k documents associated with it and their score s. Finally,
is there some beam search being used? There's a
yeah.
constraint.
So in doc ID decoding stage, we do the constrained beam search, and here we are just doing the beam search.
So this is what I spoke about at the beginning of the course also, right? All the papers you're seeing, you'll find there is an optimization during training, but also an optimization during inference. All the three papers we saw. Inference, I mean, some of the previous papers were very heavy on the inference part. So what is a constraint in the beam search? What is that constraint here?
Yeah, so actually in the generative retrieval setting, the whatever doc ID you are generating, it should map to a unique one. There should be one-to-one mapping, and it should not deviate with the already existing doc ID. So the constraint is that the model should generate a path which matches exactly with the already existing doc ID. So that is how they are doing the constraint beam search. Next slide. So this is how the entire structure of this particular framework of this paper looks like. The construction of the path set, then optimizing it with creation of the new data set, and finally how we are inferencing it and re-ranking it, and finally fetching the document. So yeah, so this was this paper. So like basically in this paper so like every generative retrieval needs three core capabilities. First is the memorization loop. It basically store and maps each document to its unique identifier for faster retrieval. And second is the generalization part. It basically understand the user query beyond exact words to infer relevant information. And third is the relevant scoring. In this, it basically ranks the document based on the importance to the query for accurate retrieval.
So this is what I was also commenting in the previous presentation, right? If you get bottlenecked in the first two stages,
Yeah.
especially the first one, I mean, retrieval will make no sense at all.
Yeah.
So I think that's a general critique. How robust are they in the first two stages?
Like this paper will basically present the framework to improve these two parts. Next.
Yeah. Also, your project, you should make sure it's relatively free from that critique, right? So
Yeah.
you should not follow the same trap.
So basically, to improve these three capabilities, it follows a two-stage training framework. In the stage one, it is basically a supervised fine-tuning stage. In this, we basically try to train the model to map input to the relevant FIDs using the synthetic data. This stage basically focus on the memorization and the generalization part of the model. Like to improve these capabilities, like we are using context and the multi-granular synthetic queries to improve the signals, basically to improve the relevant signals. And there is a second stage, preference learning. In this, we basically refine the model to rank the document using an RPO loss function. I will explain this in the next stage. So in the SFT data strategies, there are two components. First is the context to ID data. In this, we basically breaks the document into chunks and then use an LLM to pass those chunks to an LLM and generate the relevant doc IDs for those chunks. And then we pair those chunks with the respective doc IDs to train the model. So this part basically enhances the memorization part of the model, generative retrieval model. And the second core component is the query ID. In this, we basically train the model to generate relevant doc IDs using the queries. For this, we use multi-granular queries. This consists of chunk level query. We basically like provide the LLM a chunk of the document to generate some queries, and then use this query in the training stage. And there is a sentence level query. We break the individual sentences, break the chunk into individual sentences, to pass those sentences to an LLM to generate the queries. And there is a constraint based query. In this, we are generating queries while enforcing the model to include some specific keywords or metadata of the document. And after that, we map those queries with the respective doc IDs and train the model. So this is the SFT loss function that they've used to basically train the model on these synthetic data.
But it is not. So what is it doing? It's maximizing likelihood, but there's also the negative term. The two terms. What
yeah, first term is basically to improve the generalization part of the model. We are using the synthetic queries to generate the relevant doc IDs. This part basically improves the generalization of the model. And the second term is basically improving the memorization part of the model. So in this, we are using a context. We are providing context, and then from that context, we are generating the doc IDs. So the objective of this loss function is to maximize the likelihood to correct document generation, doc ID generation.
So should we not consider? I mean, maybe again for your project, at least for the generative part, why don't you try and generate for those which exist already, right? Can you do a contrastive learning there? I mean, there is a memorization part and there's a generation part, right? I mean, the first part is the generalization.
Yeah, first part is generation.
But why can't we have a generation part, synthesis, even for that which is being memorized?
Like in the RP loss function, they are using positive and negative candidates using rank those documents.
And you'll rank the ones in your data set higher than those which are generated. Some kind of contrastive.
Yeah, some kind of, but using a log like. So this is the second stage. It basically improve the reference learning, improve the ranking performance of the model. In this, we are first generating the challenging queries that are difficult to answer, but we ensure that these queries remain answerable to the model. And there is a candidate selection part. For the loss function, we need three parameters. First is the query and the positive and negative document candidate. So the positive candidate is basically the document that is being used to generate the query. That is the we can directly use that document that is being assigned as a positive candidate. To select the negative candidate, what we are doing is we are using the same model, SFT model, after the stage one to retrieve the documents using the query. And from the retrieve results, we are choosing the top negative candidates that are ranked higher than the positive candidate. If the positive candidate is ranked top one, then we neglect that. We do not include that query in the preference learning dataset. So after that, each negative candidate is paired with this positive candidate to generate the preference learning dataset. So this is the RPO loss function that they're trying to optimize. First term is directly taken from the DPO direct preference optimization. In this, we are we are encouraging the model to generate the positive candidate doc IDs for the positive candidates, and while discouraging for the negative candidates. And there is a regularization term also for which is used to prevent the over optimization of the negative candidates. And also it helps the model to basically retain the information that is being taught in the stage one. So the model does not lose information after this stage. So this is the overall framework of this table. First, there is a corpus. Then we pass that corpus to an LLM to generate the basically synthetic data for the SFT stage. There are two components: context to ID and query to ID. And using the same LLM to generate the synthetic data for the preference learning state. And then we train the model using the SFT data. After the SFT data training is done, we are using the same model to retrieve the results using the query that is being used for the preference learning to generate the preference learning dataset. And then we basically use that preference dataset to optimize the model using the RP loss function.
So the only difference in SFT and preference learning is the negative sampling.
Yeah. We are also include the challenging queries.
So you see, basically you're doing SFT to do negative sampling.
No, we are using SFT to retrieve the results. To retrieve the negative
which is used for generative generating the negative samples.
Yeah, we are using the results to.
That's the main purpose of SFT.
Yeah, improve the basically improve the relevance scoring in this preference learning. Next slide. So these are the results from the paper. They are using two datasets, multi-hop and NQFI. So SFT is the stage one model that and these and the last three are the stage two models with different configurations. as you can see, there is an increment in the like in the every parameter, in the every basically every metric. There is an improvement in the top 10 negative. Like as we are increasing the budget for the top K negative candidates, we are seeing an improvement in the in every parameter.
Uh, Hello. Hi, I am Ashish Prasad, and today I'll be talking about generative retrieval meets multi-graded relevance. So in previous works, the relevance order of documents are not specified. I hope I'm audible. Yeah. So relevance order of documents are not specified. Now, for example, if I have to search something related to gradient descent, then obviously a document which is related to optimization should be given more preference as compared to linear algebra. So this kind of thing are not much in the literature. Also, relevance cannot be simply obtained by multiplying the probabilities of each token because the length of doc ID may vary. So if there is a doc ID with higher preference, but if the number of tokens are high, then its score will be less. And also, I'd like to just introduce this term. Grade is the relevance. So higher the relevance means higher the grade. So this term will be coming up a lot of time in the presentation. So that's why I just introduced this. So methodology, there are 3 steps. First is doc ID design. So basically, we want to generate distinct doc IDs for each document. Second is the multi-graded constrained contrastive loss, which basically captures the interrelationship between the query and the doc ID for ranking a query. And third is the optimization process, which has again 2 parts: supervised and pre-training and fine-tuning. So doc ID design. So this has a encoder decoder architecture in which the document is provided to query generation encoder and query is provided to an autoencoder, and both of them share the same latent space. And then we use the decoder to generate the same query. I hope I'm clear till here. So basically, relevance term says that the embedding of document and the corresponding query should be close to each other because both of them share the same latent space. So that's how we have defined this Q relative term, relevance term, sorry. So this similarity just captures the similarity between the embeddings. This is done for this is done for all the queries, and DQ is the set of all relevant documents for a query queue. So for a query queue, this is done, and this term basically also tries to push apart the irrelevant queries. So in this entire loss function, we are also trying to push together and push apart. Next slide. Yeah. So second is the distinctness term. So because we also want to generate distinct doc IDs, so that's why now we are trying to push away the representation of different documents and different queries. So that's why you'll see these 2 terms. Here we are only dealing with documents and queries. Now, because we are also changing the distribution of documents and queries, so we have also added this one more term. Now, this is very similar to the previous relevance term, but this we have added because we are changing here. Uh, Next slide. Yeah, cosine similarity. Yeah.
But isn't this actually in? So there seems to be a kind of conflict, right, between diversity, plus distinctness,
Mm-hmm.
and relevance. Because if you just go by relevance, I might not want diversity at all. So there's a tension there.
Uh, so could you just explain the
How
question?
do I mean, how does diversity factor in relevance? Because relevance seems to be the key
Mm-hmm.
DNA of this paper, right?
Mm-hmm. Yeah.
But diversity goes against the grain of relevance.
So
So you want diversity conditioned on relevance. So where is that conditioning coming in? I understand what you're saying.
yeah, there is a hyperparameter. Okay. Yeah, next slide. Next slide. So this is the complete loss term. So we have 2 MLE losses and 1 relevance and distinctness loss term. MLE losses is nothing but negative log likelihood of the document of the query given the document, and second is the query given the embedding of the query.
This is still not diversity conditioned on the relevance, right? This is just saying, okay, alpha relevance, beta diversity. But you would like relevance to be built into diversity also, right? Like the condition. Also, that could be part of your project also. Okay. You got my critique, right? I mean,
Yeah, some.
I can just, I mean, for some weird pathological reason, my beta can be suppressed, sorry,
Mhm.
increased, and alpha goes down, and then relevance is out of the window.
I mean, just to add, can you go back? If or so yeah, in this we are only dealing with document and query. So for example, there is a document and a query. We are just trying to push them apart. But it's like here we are just trying to push apart the documents. So if the documents are like clustered, then obviously it will be like very difficult. So like uh, I hope this like to some extent it does answer. Next. Acha. So the final doc ID design, how to generate the distinct doc IDs. So first we give the document to the query generation encoder. We get this representation. We add a random noise so that we can just get distinct doc IDs. And given the noisy embedding, we then pass to the decoder to generate a pseudo query. Now this pseudo query acts as the doc ID. And yeah, doc T5 query model is used as the encoder decoder architecture. So this is multi-graded constrained contrastive loss. Um, so it also has two terms. First is the pairwise loss. So here we are trying to capture the interrelationship between the query and the doc ID. So this is just to this measures the similarity between query and doc ID. Now this is a complex term. Can you just next slide. So basically what we do is we give the query, we give the doc ID, we embed each token, we pass it through a linear function, average pooling, and then we find the vector embedding. Similar thing is done for doc ID. Go back. Now that's what this all is. Okay, and then we just use the similarity term, which is very similar to one we saw earlier. Next slide. Next slide. And next is the grade constraint. So it says that a class higher in hierarchy cannot have lower confidence. Obviously, this makes sense. So what we are trying to do is for a given grade L, we take the maximum of the pairwise loss. Okay, this gives the L max term, and when we combine both of this, we get the MGCC loss term, which is the maximum of L pair and L max of the grade higher in precedence. So, for example, now how this works is, uh, for example, this is higher, which it shouldn't be because a class higher in precedence should have higher loss term. That's how it will have higher score. So if this is high, then it will switch to the this one, which is again the pairwise loss of uh, the grade higher in precedence. And if not, then it will just stick with the lower preceding grade. So this is how it just incorporates some sort of force which is proportional to the grade. Higher the grade, higher will be the force of attraction. Basically, if so, exactly if this is higher, then we'll try to like optimize this function. So this has to be low. For the highest grade, this has to be the lowest one. So that if if for higher grades, the query and the doc ID should be close to each other. Okay, this is what L pair is, right? So for the highest grade, this has to be the lowest. Otherwise, it won't ever optimize this one, which is the lower preceding grade. That's how it incorporates the force of attraction. Is this clear or should I be? Next slide. So yeah, this is the final loss term, which is supervised. So we have this MGCC loss term with two MLE loss terms. Now, for this MLE loss term is pretty simple, given the document, what is the ID? And this one is given the query, what is the ID at LH grade, which is basically if you take a query for a given query, for a given grade, for a given ID in that grade, what is the negative log likelihood of this?
But what about multiple IDs which are in the same grade?
Yeah, so this is being done
Acha,
here,
so
right?
you're saying
So
the
that
max
is
part. What about the max part?
max part as in this one.
Yeah, L max.
So
Will you break ties arbitrarily here?
sorry.
L max.
Mhm.
Uh,
For a given grade L, for a I guess it's also for given query. I have not mentioned it, but it takes the maximum of all. So the maximum should be lowest. for the highest grade.
Yeah, but what I'm saying is the maximum itself, there's a tie. You just break it arbitrarily, is it?
Make a tie in the sense there. Acha, this so that was not
Just break
mentioned. So
it
I
up.
guess yeah, arbitrarily I guess. Next slide. Next slide. Yeah. So pre-training. So here they use Wikipedia articles. The queries become the random sentences from the abstracts. I'm assuming they must be using some LLM here. Okay. There are 4 grades of relevance. Grade 4 is the highest grade, highest like relevance. So original article containing the query, and that's how they go down to each grade. So grade 1 is an article linked from the anchor text, which is like hyperlinks you find in the Wikipedia article. Then you train the model on this data set, apply the same loss function. That's how you get it. If you can go back, thoda sa. Yeah. एक और पीछे. हाँ. In this one, I just wanted to add something. This they have used this method, but there is one more method that could have been used. So if you can just weigh it, you can take a weighted average of the loss, pairwise loss for a given grade. That could have also worked, but yeah, it's not very clear why they have used this and not that, because I'm sure if I can think this, then they must have also thought about that.
Yeah, that's a good critique. I mean, I don't know if in your what's your proposed work. Maybe you should skip the experimental details and go to your proposed work because we are out of time. Oh, you don't have any proposed work?
Yeah. Yeah.
TSGen, which works on the term side generation, and it is like it uses tag data for doing everything. Even take the ideas, but like maybe the path from the first paper, the second paper, and third paper, how they are trying to weigh on and then improve the term side.
So basically, for all this, MRR score is like one of the most used metric. And if we use this grade 1, so it can directly improve the MRR. But obviously, like it just ranks the perfect. So, no.
But it may not do great on map score. MRR is mean reciprocal rank. But it may not do very well on mean average precision.
Yeah,
It's a trade-off always.
yeah.
So what's your idea to optimize MRR or map? I mean, what do you want to
I guess it should be MMR.
MRR?
MRR.
So you want to stick to this. But what is a
Like,
so auto AIs? That's the holy grail for you. Auto AIs. You could have put one slide on that. I mean, what you want to do as part of project. Everyone should do that. In fact, everyone should also, as I said, let's make it a policy. Everyone's paper should be on archive by the end of the project. Okay, Isha let's put a post. Everyone's paper should be on archive by the end of the project.